Hey there, Chem fans. Welcome to our AP review for topic 8.2, pH and pOH of strong acids and strong bases. So before we can dive into this particular topic, how to calculate pH and pOH, we need to make sure you understand what a strong acid and a strong base, what each of those are. Strong acids, such as hydrochloric acid, which is one you're very familiar with, when it's placed in water, every single molecule of the HCl will dissociate or ionize into H positive ions and chloride ions. In other words, if we started off with 30 molecules of HCl and put them into water, then those 30 molecules will all split apart into hydrogen ions. So you'll have 30 hydrogen ions and chloride ions. So you'll have 30 chloride ions because each HCl breaks apart into one H and one Cl. So 100% ionization is what makes something strong, what makes a strong base strong, or what makes an acid strong. So how do you know what the strong acids are? Well, you have to memorize them. There's no shortcut to that, and there's only 6. HCl is one of them. HBr is another one. HI, nitric is another one, nitric acid. So hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, perchloric acid, HClO4, and then last but not least, sulfuric acid, H2SO4. So all of these acids will 100% ionize into its ions when placed in water. And that's what makes them strong acids. What about the strong bases? What makes a strong base a strong base? Well, one strong base you're probably quite familiar with is sodium hydroxide. And sodium hydroxide will 100% dissociate into its ions when placed in water. So the sodium ions will break apart from the hydroxide ions when they're placed in water. You know this already because sodium's an alkali metal, and anything bonded to an alkali metal when placed in water is completely soluble. So sodium hydroxide, just like sodium bonded to any negative ion, is going to be 100% soluble and dissociate 100% into its ions. So again, if you started with 30 formula units of sodium hydroxide, put them in water, then those would completely break apart and you would end up with 30 ions of sodium and 30 hydroxide ions. So how do you know the strong bases? Well, again, you have to memorize them, but these aren't too bad because the alkali metals bonded to hydroxide are strong bases. So lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, and cesium hydroxide. All of those, when placed in water, will dissociate 100%. What are the other two? There's two more hydroxides, and they are alkaline earth metals hydroxide, way down at the bottom of the alkaline earth metals. So barium, when bonded to hydroxide, dissociates 100%, and strontium, when bonded to hydroxide, dissociates 100%. So these are your strong bases. And again, it's all based on, do they dissociate 100%? So that dissociation is what allows us to calculate the pH and pOH in a very simple way. When we get to weak acids and weak bases, that's going to be a little more complicated. But with strong acids and strong bases, it's actually pretty easy. So how do you do it? Well, let's look at an example. Let's say we had a solution of HCl, and that solution was 0.03 molar. And of course, if the HCl is dissolved in water, then it's going to dissociate 100% into H positive ions and chloride ions. So when we say it's 0.03 molar HCl, it's not actually 0.03 molar HCl because all of the HCl is going to break apart into H positive and Cl. So you really don't have 0.03 molar HCl, you have 0.03 molar, because it's a 1-to-1 ratio, hydrogen ions, and 0.03 molar chloride ions, because it's also a 1-to-1 ratio. So all of the reactant is going to become products. And now, since we know the concentration of the hydronium ions, the hydrogen ions, we can calculate pH very easily because pH is equal to the negative log of the hydronium concentration. And remember, we can write hydronium as H positive or H3O positive, either way. So if we know the concentration of H3O or H positive, then we can calculate pH. Notice if the HCl does not break apart 100%, if we had a weak acid, then we wouldn't know the concentration of H positive because some of the weak acid wouldn't have broken apart. HCl does. All right, so we plug in our concentration of hydronium, which is 0.03 molar, and we take the negative log of that, is 1.5. Notice there's one significant digit in my concentration, and for pHs, for logarithms, only the numbers after the decimal are significant. So there's only one number after the decimal, so this has only one significant figure. The one in front is not significant. So the pH is 1.5. So that wasn't too bad at all. Knowing the concentration of the acid tells us the concentration of the hydrogen ions. We can also calculate the pOH by using the equation pH plus pOH equals the pKw, which if this is 25 degrees Celsius is 14. If it's not 25 degrees Celsius, it would not be 14. Since I don't have a temperature here, I'm going to assume that it's 25 degrees Celsius and 14. So we plug in 1.5 plus the pOH equals 14. And so 14 minus 1.5 gives us a pOH of 12.5. And that's it. So that's how we calculate the pH or pOH of a strong acid. Now, please note, it's a 1-to-1 ratio between the acid and the hydrogen ion concentration. H2SO4 is diprotic, and that starts getting a little more complicated in how it deprotonates, how the hydrogen ions come off. Because with a diprotic acid, the first hydrogen comes off 100% and makes HSO4 negative, but then that second ion will also deprotonate and lose its hydrogen, which will contribute some hydrogens to the acid and make it more acidic. That is more complicated, and that starts getting into weak acid territory, and so we're not going to do any calculation with H2SO4. Same thing with the bases. We're only going to look at monoprotic bases, bases that only accept one hydrogen ion or only lose one hydroxide ion. So let's look at bases. How do you calculate the pH or pOH of a strong base? Well, very similar. If we had an NaOH solution, that NaOH solution 100% dissociates into sodium ions and hydroxide ions. 100%. So if this was let's say a 0.30 molar sodium hydroxide solution, then it actually doesn't have any sodium hydroxide bonded together in the solution. All of that sodium hydroxide dissociates in a 1-to-1 ratio and becomes sodium ion, so that becomes 0.3 molar, and hydroxide, which also becomes 0.30 molar. So now we know the hydroxide concentration. And if we know the hydroxide concentration, we can calculate the pOH using the pOH equation. pOH equals negative log of the hydroxide concentration. So we just have to plug in the 0.3 molar, so negative log of 0.30 molar. You get 0.52 for the pOH. Notice there's two significant digits in the concentration, and so I have 2 decimals in the pOH because only the decimals are significant. As far as pH, we just used the same equation earlier. pH plus pOH is equal to 14 if this is at 25 degrees Celsius. So we plug in 0.52 to get the pH. So when you solve for the pH, you get 13.48. And that's it. That's how you can solve for the pH and pOH of strong acids and strong bases. Again, this works if they're monoprotic. If they're diprotic, that gets a little trickier. But we're going to stop there. If you have any questions, feel free to ask me. I'd be happy to help you. And good luck in your studies. Bye-bye.